In this unit, we'll go over what's called the standard form of a linear program. The problem data consists of one matrix and two vectors. A is n by m, B is n by 1, and C is m by 1, and they appear like this. The decision variable to be found is x, which is an m by 1 vector. And the problem defining the goal is to minimize C transpose x subject to ax less than or equal to b. So this problem is characterized by an objective function, C transpose x, which is linear, and constraints, which consists of many different linear inequality constraints. Remember that this less than or equal sign is applied element-wise to all the components of ax and all the components of b. So with this setup, the red box is called the standard form of linear programming. If we look at the diet optimization problem, it didn't appear to be exactly in this form. Let's see how we can transform it to this form. First, let's remember what the identity matrix is. For any integer k, the k by k identity matrix is the square matrix with 1s on the diagonal and 0s elsewhere. The most important property of the identity matrix is for any k by 1 vector v, identity times v, which is the array consisting of 1s and 0s, times v, and if we follow the matrix vector multiplication rules, we simply get back v. So identity times v always gives back v, regardless of what v is. In MATLAB, the identity matrix is created with the I command, EYE, and then the dimension desired. Let's now see how we can transform the diet optimization problem into a linear program in standard form. The diet problem as formulated does have a linear cost, but the constraints look slightly more complicated than the standard form constraints. Here's a matrix identity which will help us. Let's actually work from the right. Consider the array V vertically concatenated with the identity array, and multiply that array times the vector A. Remember that this matrix vector multiplication can be thought of as vertically concatenating different linear combinations of A, the linear combinations coming from the rows of V and the rows of the identity matrix. That's equivalent to the middle expression. There, the matrix vector multiplication has been done individually and then vertically concatenated, which is the same quantity. And finally, the identity matrix times A is simply A. The original diet problem constraint imposes that the elements of VA are greater than or equal to R, and the elements of A are greater than or equal to 0. That simply means that the array VA above A is greater than the vector R above 0. Therefore, let's rewrite the diet problem like this. Still the same linear cost function, subject to V stacked above identity times A greater than or equal to R stacked above 0. We're almost there, except the standard form has a less than or equal sign. So let's switch the signs using multiplication by -1. There, linear cost function subject to a single array times our decision variable less than or equal to a vector. That is the diet problem in standard form. Matching, we see that this is the array A, this is the vector B, and P is the vector C. The decision variable A becomes the standard decision variable X.